Hey guys, what's up? Eddie Alho here with KissAnalog.com. Follow up to Inrush current measurements. I want to just cover this again, just a little bit more. I had one of our watchers, David, ask a good question. I think he felt a little lost, and this can be a little bit of a complicated measurement, and that's why I kind of brought it up. I think some people don't realize how complicated it can be, and that's why I brought it up. These power supplies I have are nice, and by the way, I'll let it run. Anyway, these power supplies are nice, but you know, they're limited. They're limited in current, and usually a power supply, I've designed power supplies where I give them to a guy who I've designed it for. He hooks it up to his product, and then he calls me down in the lab, says it's not working, and find out that his lab supply has a current limit. So maybe it's a 100-watt power supply, and he has, say, 25 volts input, so he figures 4 amps, 100 watts, okay, and then he gives it another amp or two and figures that's good, you know, it should run. But when he brings it up, it doesn't turn on, and it turns on, turns off, turns on, turns off, and he thinks the power supply isn't working right, when in fact it's the lab power supply. It's current limiting, and so you have to turn off the current limit, or turn it way higher. So if the normal current's 4 amps, you might need 20 amps at the input just to start it up. The reason why is when a power supply first turns on, if it's designed to say that it's operated at 25 volts, well, it's really going to operate over a wide range, right? And maybe it turns on at 20 volts. Well, 20 volts is going to take more current. Not only that, the switching power supply is on, off. And let's say it's on, off half the time. Well, that means half the time it has to supply twice the current, so the average current is what you want. So if the average current's 4 amps, it really has to supply 8 amps during the time it's on, so during the time it's off, it's not supplying anything. So now it gets worse than that, because the power supply, when it first turns on, it might turn on for just 20% of the time. Well, imagine that. Now it's got to be 5 times the current, so 20 amps. That's why it can be that way. So a lot of times we design power supplies to have a soft start, but if somebody brings up the voltage slow, that's slower than the soft start. What a soft start does is it allows the power supply to put out small pulses without current limiting, and it ramps up the capacitors on the output, ramps up the load, okay? So when you first turn on the power supply, it has to charge up all these capacitors, and capacitors look like it's short until they fill up, until you charge them up. Once you charge them up, then they hold your voltage. They try to, you know, filter your voltage, try to keep it flat. But initially, you know, they have to charge up. So 2 inrushes, I think I pointed them out before. One is when you first plug it in. When you first plug it in, you're going to get this gigantic pulse. Then once the voltage comes up to where the power supply is going to turn on, say in this case just over 10 volts, then it's going to start switching and turn on. But when it switches, and it's, let's say it's drawing 20 amps, and this guy's only capable of 6 amps, well, this guy's going to current limit, so he's going to struggle. So that's why he kind of struggles. But eventually, hopefully, you'll charge up the capacitors a little bit on the output, and it'll kind of staircase up until it charges them up enough, and then it'll run, okay? So there's 2 problems, 2 issues here. One is the switching power supply struggling against your lab supply, and the other is that gigantic current inrush when you first make your connection. So if you take a switch like this and just switch it on, those contacts inside are going to see this big spike of current, okay? Not only that, your capacitors are going to see a big spike of current, because they're saying, hey, I'm short. But they're not really short. There's some ESR in there, some equivalent series resistance, and that current spike in that capacitor may not like it. Aluminum electrolytic, they may not like it. Ceramic caps may not care. wet slug tantalums, they may not care, but aluminum electrolytics, they may care, and they may get wore out quicker. So every time you pulse that current on, you know, you're hurting it. So if you think about light, an incandescent light bulb, usually they pop when you turn the switch on, right? That's usually when they go. How many times has the light been running and then it just die? It can happen, but not very often. Usually it happens when you first hit that switch on. Why? Because that element inside that light bulb is cold and the resistance is high, and when you hit that switch, the current, the voltage instantly hits that and tries to heat it up super fast. And when it does that, it's just charging, it's just heating that element so fast that sometimes they pop like a fuse. Once they're up and running, they're hot, and they actually, you know, just run hot. They change electrical energy into thermal energy. But yeah, anyway, so that's why I talk about these thermistors. That's a cheap, easy way to do it. Another way to do it is in your electronics, in your design. But this is a simple, pretty rugged way of limiting the inrush current. Okay, so I hope this video makes a little more sense. I'm going to show the setup a little bit better, and I'm going to show some more pulses here, and I hope that I help make this understandable. Okay. Hey, thanks for asking the questions, guys, because if one person asks, it means there's probably another 10 that didn't ask. And you know, maybe somebody gave me a thumbs down because they were so confused. They just thought, oh, this sucks. So that kind of sucks. I'd rather them ask a question so I can try to respond. But anyway, I'll try again if this isn't understandable enough. And by the way, I've got some inrush. I did another inrush current measurement on an earlier video on a power supply design. So this subject will actually continually come up. You know, as I do reviews of power supplies, I'll take these inrush measurements so you'll see it over and over and over, and hopefully that makes more sense. As far as the second inrush problem, that going into the load with the switcher power supply, let me just try to cover it another way. Let's forget about the switcher, okay? Let's think about a linear power supply. When you first turn it on, you're going to get this inrush current through to the capacitors. Then you'll get one at the same time kind of through this transformer. And actually, that's one of the videos I've done is something about, you know, the transformers inrush current. So that's something to look at. That might help a little bit. But anyway, even with a linear power supply, this magnetic structure has to build up a magnetic field. That happens quickly, and it creates kind of a inrush current issue. So this, capacitors, and then once you go through your linear power supply, you have load, right? And the load is all of a sudden you're going to go from, you know, 0 volts to you turn on, let's say you're regulating 5 volt output. That 5 volts kicks on, all your digital chips or whatever you're powering turn on and start running. So when all those things turn on, it's just like if you think about, you know, if you're, let's say you have a microwave turn on and you've got a washing machine running, and you know you have a lot of things running, and you turn on one more thing, and that inrush current to that thing, you know, it's just kind of an overload. So okay guys, hey, I hope this helps, and thumbs up to David for asking the question. Thanks guys, thanks for watching. Okay guys, let's just do this one time just to see if we can bring everybody up to speed here. This is a boost converter, okay? It takes in voltage on this side and puts out voltage on this side, okay? We're going to monitor the input voltage here, and we'll look at the output voltage on this meter. So this is input voltage and this is input current. So I have this Handtech current meter right now plugged into here. Oops. See, Here we go. Put them up here so you can see them. Sorry. So I've got that plugged right into here, and it's on volts. Now the thing is this is a 10x thing, 1 millivolt for every 10 milliamps. So that means that we'll multiply this by 10, and that'll tell us how much current we have, okay? And then this input voltage, output voltage, like I say, the plus voltage here, plus ground, output, the load is plus, ground plus. This goes to an active load that I have set up for 30 ohms right now. Okay? Whoops. Okay, so this is going to 30 ohms. Okay, this is going to 30 ohms. And the voltage will come up to about 28 volts here. Sorry, get that out of the way. So this cord here comes over and plugs into here. Alright, from the Handtech. And this this cord here is coming underneath the meter and comes up here, and so we're reading the voltage right here at the output. You can see that here, and this red and green leads from this meter are plugging in here. Let me come back here a little bit. Are plugged in right here on the input voltage, okay? Oops, this guy fell asleep on me. So that guy. Jeez, wake up. Alright, so we got the, here I'll slide this up a little bit. Okay, so we see the setup, okay? So what I'm going to do, I'm getting a little bit of a glare here. And get the screwdriver. I was trying to prop it up so you wouldn't glare, but that made it glare worse, I think. Alright, so here we go. So I'm going to recharge the power supply and I'm going to start cranking it up. Try not to get in the light here, which might be impossible actually. Here I'm going to have to reach over here. Okay. Here comes the voltage. I'm up to about right there, 5.8 volts. The output, now on a boost converter, the input voltage, the input voltage over here, sorry about that, the input voltage over here goes straight through the power supply with just a little bit of a drop because of the diode and the inductor. That's the way a boost converter works, okay? So, shoot, I don't know what meter that is. I think it's this one. Okay, so right now the power goes straight through to the 30 ohm load, so we should see a little bit of current here, and that's really 90, remember that's 10 times, so that's 94 milliamps right now, okay? So that's going to the load right now. So we bring it up, voltages, okay, there we go, we're high enough to output voltage jumped up, so now it's the boost converter is running. So out 28 volts into 30 ohms, and we only have 12.7 volts in the input. So I'll just bring that, well, you can see the current. Now remember that's 10 times, so that's 2 amps, 2.1 amps going into it, okay? So now watch, as I bring up the input voltage, so if you think about the power right now, 12.6 volts times 2 amps, we're about 24 watts, right? Roughly 25 watts, you know, something like that. Now as I bring up the voltage, let's say if I come up to, you know, I was going to say if I double the voltage, but if I bring this up to 19 volts, then this current's going to drop down because we're supplying the same power to the load over here, okay? Okay, watch this. Okay, so we have 19 volts in. Now for some reason, oh, I bumped my probe here, sorry. This isn't making a super great connection. So that's 1.26 amps going in. Okay, 1.26, 19 volts, and 28 volts output. And that's a 30 ohm load. Okay, so we have almost 30 watts. That's almost 20 volts times, you know, that it's, you know, so the input power's we have some efficiency loss, so we have some power drop. Now this runs pretty cool at 20 watts. Okay, now here's the thing. I brought up the voltage slowly, right? If I brought up the voltage really fast, this power supply, that's the input capacitor right there, and that's the output capacitor. Now remember, the voltage runs right through even when the boost isn't running. So that input is connected right here. So when I instantly put voltage on that capacitor, it looks like it's short and it has to charge up. Okay, so when it does that, it draws a lot of current until it charges up. On the output, we have an inductor and a diode that's on this heatsink in the path. So it's going to drop a little bit of voltage, but otherwise there's going to be an inrush current going to this capacitor as well. So we have inrush to this one and to this one. Alright, that's the thing about a boost converter, is output's actually connected even when the boost converter is not running. So when we initially plug it in, we get this spike of current to charge the capacitors. So that's one inrush current. The second inrush current is once that boost converter bumps up to 28 volts, instead of say 9 volts or 12 volts, once it bumps up to 28, it's going to charge that capacitor again. Not only that, the load, it's going to supply even more current to the load if it's a resistor. Like in this case, I have a 30 ohm load. So, you know, if it's only, let's say it turns on at 12 volts, then 12 volts at 30 ohms is, you know, not a lot of current, say half an amp roughly. Well, at 28 volts, it's closer to 1 amp. So when this boost converter turns on, when it goes, you know, when it jumps up, when it tries to climb real fast, it's going to have an inrush current. Now the problem with inrush current, especially that spike, is if your power supply that is on the bench that's powering this thing, if it's not capable of supplying that spike of current, then it'll go into current limit. Not only that, if you're using, let's say, a switch, you know, let's say you have, let's say you have a switch here and you turn it on this way, boom. Well, the contacts in there have this spike of current, and as the contacts touch, it can put a little pit, a little spark into the contact, because it doesn't instantly just, you know, when you put the contact down, these connectors just don't perfectly touch and don't bounce. They do bounce just slightly, and that can cause a little bit of arcing when they do that. So that spike of current to charge these capacitors, also these capacitors have some ESR. They may not want to have voltage instantly applied. That could wear them out too, as well as other things that are in the path. Maybe, I got big heavy things here, but maybe the trace going from here to this capacitor doesn't like to have a lot of current. You know, there's things that can, you know, you can cause issues with inrush current. Mainly the lab supplies. I can't tell you how many times when somebody who I've designed a power supply for says that my power supply is not working, and when I go to the lab I find out their lab supply just could not supply the inrush current, and so they had the current limit on their lab supply turned down too low and it was tripping the current limit. Okay, so here, I don't know if this meter, let's see what that meter looks like when I'm going to pull out the banana jack out of the power supply. The voltage drops. This discharged quickly. That 30 ohm resistor discharges the capacitor quickly. Now, this has some residue current, this Handtech. It's a magnetic coupling up here, and so there's some residue energy. So I just have to hit this, see how it zeroes out the meter. I just hit this a couple times and it degausses. It runs some AC electricity through the coil, and it demagnetizes it. It's called degaussing. Okay, see, it's practically zero now, right? Okay, now I'm going to take the power and I'm just going to plug it in and watch this meter here to see if the current jumps up. As a matter of fact, I could probably set this to max and see if I can capture a maximum reading, okay? So see that? It's set to max. Let's see if it captures it. It might be way too fast for this meter. Alright, so remember that's multiplied by 10, so it's 1.7 amps. Well, I know it was a lot higher than that, so here, let me turn off the max. Now it says min. I'm going to hold it down. I think that's how you turn it off. Or maybe I just toggle it. Okay, I toggle it. Okay, now it's 150. So it kind of jumped up a little bit. You know, this meter's just way too slow. You have to use an oscilloscope to capture it. So you have to use an oscilloscope to really capture that, okay? Alright, so you see the setup, and right now I'm using this to measure the current. Now I'm going to go back to the scope one more time just to show it real quickly on the scope, okay? Alright guys, so I moved the meter over here. Here's the input voltage. Right now it's almost 15 volts, right? And here's the output voltage, 28 volts. And here's the crazy power supply just bouncing all over the place. Here, I'm going to freeze it for a second. Okay, so that's the voltage on the boost converter. Don't have to worry about that right now. We're just talking about current, okay? So the current, you can see right here, that's where it's that's reference point, okay? And it is 1 amp per division. So we have about 2 amps, and you see it's kind of a wavy. So about 2 amps, and it's got all this noise on it because the switcher, every time it turns on and off, kind of creates a noise spike. Plus my voltage probe, I'm not doing anything to try to limit the noise right now. I'm just trying to look at the current level, okay? Now, the reason it's bouncing around, I'm triggering off the current, and the current's bouncing around. Watch this. If I turn the time base, so I'm looking at a whole bunch of time, see how the average current's doing this kind of thing? So it's just kind of bouncing around. If I turn the current down like that, you see how it's just kind of bouncing all over? So it's hard to get a good trigger when it's doing that. And that's why it's kind of shaking. And the scope's real fast, so it captures a whole bunch of images and puts them on top of each other. That's why it looks like they're, you know, that's why it looks so bad. But when I freeze it, it just saves the last image. Okay, now watch these things and watch this current. Okay, I'm gonna bring this current back to, okay, that was 5 amps. I'm gonna go back to 1 amp per division. I'll go a ½ amp per division, okay? And here now, watch, I'm gonna bring the voltage down and wow, hold on a sec. Okay guys, so I've moved the meters. This is the input voltage. I've got 11.7 almost volts there and 28 volts on the output, okay? This is power supply running. It's half an amp, 500 milliamps per division, and it's referenced right here. So it's 1, 2, 3, 4, 5. Okay, right here you can see it says the peaks are like around, well, it says 4 amps. That's this noise spike. Alright, so, but you can see it's like 1, 2, 3, 4, 5 divisions. That is with the 30 ohm load. This is the boost converter, the waveform on the FET turning on and off. Okay, this just rings, so don't worry about that. Let's just talk about the current for now, okay? I have a video on the boost converter, but let's just look at the current. Okay, now I'm going to go ahead and bring up the voltage, and you'll see the current level kind of drop. Okay, because that's the input current, and as the input voltage goes up, the current will drop. See how it's dropping? Whoops. Now it's kind of, okay, let me get up to 20 amps or 20 volts there. Now what's happening is there's not very much load, so it's turning on and off. So there's actually, see how it's turning on and off? So yeah, you see that. So the currents drop down because it's easier to maintain this thing with this load. Now if I bring the load up a little bit, uh-oh. See, if I go too far, I'll go into current limit. But see, now the load's up I've got 10 ohms, so I'm at 75 watts. Okay, so kind of off scale here. Okay, so now I'm 1 amp per division, so it's 1, 2, 3, about 4 amps. Still kind of bouncing around a little bit, but okay, so here's the thing. So there's the current, and I got 20 volts in, 28 volt, about 20 volts in, 28 volts out, right? Now I'm going to put this in single mode, so it'll trigger just one time, and I'm going to pull the connector out of the power supply. Okay, so right now there's nothing happening, no voltage at the input, no voltage at the output. This image is froze, so I got to hit the single again. Alright, so the scope's waiting for something to happen. And I'm going to plug this in and see if we can capture how much current rushes into those capacitors. Well, actually, little problem here. See that arrow right there? The trigger is off the screen, so I come over here for this position button and push it in, and it centers it in the middle. So I'm going to start off there, put it back in single mode. Okay, ready, set, let's get some voltage now. Okay, plug that in. Alright, see the current coming in? Now look, 20 volts, 28 volts out, but see the current was 0, and then it just shot up, went right off the screen. So that's 1 amp per division. 1, 2, 3, 4, 5, 6, 7. So, way more than 7 amps. So this power supply could handle that, but it does kind of cause an arc in that. The way to limit this problem is to use, what I've shown in some other videos, these thermistors. This guy right here, it looks like a resistor until it heats up, and then it drops down to real low ohms. And then it lets the current pass through. Okay, but that's so you don't get these big spikes. Now watch, I'm going to change this current to say 10 amps per division. See there, it dropped down. 10 amps per division. Okay, let's hit single mode. Well, I got to disconnect the power supply. Okay, capacitors are discharged. Put it in single mode, and I'll do it again. Didn't capture it. Okay, let me see. Sometimes you have to play around with these the current level to get it trigger right. Okay, let me see if I can capture it now. Here we go. Okay, so I captured 2 spikes there. I'm going to disconnect the power supply. So you can see it came up. Okay, I'm going to disconnect it so we can discharge caps and get ready to do it again. So we had this spike. That's 10 amps per division. 10, 20, 30 amps. And I kind of bounced when I put it in there. Same thing, same kind of thing might happen with this. Okay, so it causes arcing when you do that. So so we got 10, 20, 30, 40, 50 amps here. So that's a lot of current. Some power supplies might not be able to handle that. Okay, now if I squeeze these together so I can collect more information, and also see nothing's happening here until it triggers, so if I move this trigger over here I can capture more stuff. Let's just do that. I'll move it over right about there so it's on that grid right there. Okay, goes single mode, and I'll plug it in again. Now that's 100 microseconds. This capture even more. There's 200 microseconds, there's a half a second. So I'm going to move it back over there. So, 500 microseconds. Okay, here we go. Ready, set, go. Wow, look at that spike. Way off the screen. Okay, whoops, this turned off. So we got 20 volts in, 28 volts out. Now, the thing is this is 10 amps per division. Went 10, 20, 30, 40, 50, 60, 70. Let me see if it clipped it. Oh, it looks like it might not have clipped it. See that? Here, I'll spread it out a little bit. Well, here, let's zoom in on it. Alright, so this is 20 amps per division. It's 20, 40, 60 amps. See right here, 60.4 amps. That's a lot of current. And by the way, Here, let me disconnect my current hand tech. This hand tech is rated for 65 amps. So I think the hand tech is getting, I think there's actually more current than that. So I can only measure up to about that much. I'd have to do another way to measure it to get the real amps, but I'm just kind of giving you the idea of how to do it right. If you have a, I'll have to show you a trick on how to do it with a meter like mine that's limited to see if that's the problem. Let's just try to capture one more to see if that's what's limiting me. Okay, disconnect the power supply, let it discharge. Okay, ready? Here we go. Ready, set, go. Shoot, didn't trigger. All right, let's try that again. Ready, set. Oh, come on, trigger. Okay, here we go. All right, let me adjust this again. Okay, ready, set, go. There we go. Come in, pull out the power supply, let it discharge. Okay, 20 amps per division. So right there, 64 amps. Or is that 54? That's 54. Okay, and right here is about 20, 30 amps. So the other thing to notice is even after that spike, this is the 30 ohm load. Well, right now I'm at a 10 ohm load. So that's still supplying a little bit of current to the load, and the boost converter is not turned on. See the yellow voltage on the drain of the FET? It's not switching. Now if I capture more information, oops, hold on a sec. If I squeeze this in, capture more milliseconds, okay? Here, let me hit the single button, and I'm gonna actually move this over again, back to the side. Okay, let's do it again. I'm gonna plug it in. Here we go. All right, I'm gonna unplug it. All right, so now the boost, so big old spike. You can see the voltage come up a little bit, and then there's a little bit of current flow right here. See that? There's some voltage, and there's current flow here. And this is going, because even before the boost converter turns on, whatever voltage is here is putting current into the 10 ohm resistor. And then right here, the boost converter starts to switch because the voltage comes up high enough to see 10 volts per division. Once it goes up just above 10 volts, it turns on. And then we start getting switching. And you know what? I think a lot of this current, the voltage is so low through here. See how it stays high? I think this current is still trying to charge up that capacitor on the secondary side. And then it starts to switch, and the voltage comes up, and then once it comes up, it starts to regulate, and we don't have a lot of load, so it kind of turns on and off, and then finally starts to regulate over here. And you can see the current, you know, kind of over here, it starts to come up. And now this is 20 amps per division, so it's kind of hard to tell because 10 ohm load, we're only drawing about 1.8 amp or 2.8 amps. Okay, so this can be a problem for a power supply, and also this inrush, when this thing starts to turn on, it might be fighting my power supply, because my power supply in the lab, once it hits this voltage here, it should just come right up, but instead it's fighting against my lab power supply because as it tries to come up to 28 volts, it's at the limit of the current that my lab supply can put out. Alright, so what I'm going to do is I'm going to increase the load from 10 ohms to 100 ohms, or maybe even 150 ohms on my lab supply, to see the difference that it makes when it turns on. If it doesn't have to supply so much current, my lab supply can keep up. Watch how it changes, okay? See, I'm up and running. I'm going to disconnect, and then I'm going to change the load to I think I'm going to change it to about 150 ohms. Okay, now it's 150 ohms, and let's see if I can supply enough current for this thing to come up. On a switching power supply, when it first comes up, before the voltage comes up high enough, it's taking a lot of current. Once it comes up, then it's switching less current, so the lab power supply can keep up. But during this inrush of current, when it first turns on, it kind of struggles. Okay, let's see what happens now. Yeah, there you go. See how much faster it came up? Oh, look at that. It's not even regulating very well because I don't have enough load. See, that went up to 45 volts. So now it's capable of going way up. That's not good. 45 volts on 35 volt caps. I have 35 volt caps in there. But you see how once it turned on, it just kept switching. It kind of struggled a little bit, but it came up much faster, right? All right, I'm gonna go to 100 ohms and see if I get a little bit. 100 ohms, let's see, there we go, 100 ohms. Let's see if we get a little better behavior. Nah, it's still kind of fighting it. So, see, so that's the thing. I need a bigger lap supply, even for this small boost regulator. It's just, this boost regulator does not have a soft start. A soft start allows a switching power supply to come up softly, so it doesn't create so much inrush current when it tries to boost up. So, you know, as it's going from whatever the input voltage is up to 28 volts, it has to send a lot of current to the load at 28 volts. See, once it's 28 volts, if you say you had a 28 ohm load, it's only 1 amp. But when you're at 14, it's 2 amps. But when you're pulsing, it's off half the time, on half the time, so it even doubles the current. Okay, so I hope that makes more sense.